Hello, hello. Good afternoon, Vicky. Good afternoon, Kian. Good afternoon, Mafine. Good afternoon, Joel. Good uh, hello, Anthony. Good afternoon, Roger. Good afternoon, Mafine. That's a double. Good
Good
afternoon,
morning,
Raina.
Professor.
Good afternoon, Lear with the voice. Awesome. Thank you. Good afternoon. Oh, good afternoon.
Good afternoon, Professor.
Oh, good afternoon, Victoria, with the voice. That's point. Good afternoon, indeed. Thank you. And that's points. We hopefully know. Okay, wait. Hold on. There's more. And good afternoon, Kian. Oh, with the chat and the um thing and the avatar. Right. Awesome. Good afternoon, Joel. People coming. Good afternoon. Good afternoon, Caitlin. Good afternoon, Aminata. Good afternoon, Vicky with the double. And wait, Kate, what just happened with Kate? Hold on, sorry, we're gonna get going here. Good
Good
after
morning, Professor.
Oh, and good morning, Fabia. I love that this class does voices. I love it. I appreciate it. And who did I just skip? And good afternoon, Victoria. And good afternoon. Okay, I think that's. Oh, and good afternoon, Melanie. And good afternoon, Zoe. Well, okay. And Lear and Vicky with the video. Okay. But did something just happen with Caitlin though? Sorry, we're starting. What just how did Caitlin?
Good afternoon, Professor.
Oh, good afternoon, Mohammed. Thank you for saying so. Okay. One little thing to say. Okay, we're gonna just get okay. I kind of want to not rabbit hole today. Good luck to me. Uh, so I want to get like straight back to the physics, the mathematical physics, i.e. to homework two. That's we're about to shift gears and keep going over homework two. Um, Takeaway from Monday's class is that ultimately, okay, all physics classes are about stuff occupying space and time in a measurable, reproducible, predictable way. Worth saying again, worth writing down. Like anything is physics, the province of physics, the domain of physics, what it means to study physics is to study things that occupy space and time in a measurable, reproducible, predictable way, right? So motion through space and time is what we study. Some things that occupy space and time in a measurable, reproducible, predictable way, some things occupy space and time in a very concrete, thingy sort of way. Some things are really very clearly identifiable and distinguishable from other things. Some things are material, massive, concrete, countable, and particular. We call those things particles. And what it really means to be a particle, whether you're very small like an electron or very big like a planet, what it really means to be particular, what it means to be a particle is that, not just that you occupy space and time in a measurable, reproducible, predictable way, but that if you are a particle, you cannot occupy 2 points in space at one point in time, and you cannot co-occupy, you cannot share a point in space at a point in time with another particle. That's what it means to be a particle. Anything that seems very thingy, right? Anything that you can touch or picture yourself touching or put on your desk, macroscopically observable, massive material objects are particles in this specific rigorous way that they cannot share space at a time with other such particles, and they cannot be delocalized. They cannot be in two spaces at one time. That is what it means to be a particle. There's obviously some fancier ways to put that in more scientific terms, and some of them you know from chemistry. If you think about it, the Pauli exclusion principle is a more specific, rigorous, technical way of capturing one of those two ideas, if you think about it. And if you don't, it's okay. But the takeaway from 2 days ago is that description, the idea that you cannot be in two places at once and you can't share a place at once with another such being. That, my big point is, that is what it means to be a particle. That is not true of all entities that occupy space and time in a material, in a predictable, measurable, reproducible way. My argument, or my statement is that there are plenty of unthingy things that are part of science. There are plenty of things that occupy space and time, and plenty of things that matter but aren't matter. There are plenty of phenomena that are not material, distinguishable objects. Those such things include waves on a string, waves on the water, sound waves, electrostatic fields, electric currents, magnetic fields, gravitational fields, and electromagnetic radiation, otherwise known as light. That hopefully I gave you that list, or you wrote that down Monday, or maybe, or if you want me to say it again, I will. But that list of things that I just named was not an arbitrary list. That's the things that ultimately we study in this course. Ultimately, this course is still about stuff moving through space and time, but it's about stuff that is not particular. Physics 203 was about the trajectories of particles. Physics 204 ultimately is about the flow of information. All those things that I just named, whether the sound waves, electrical currents, electromagnetic radiation, i.e. light, what they all have in common is, I would argue, or I would say, all of those, what they are different forms of information that can occupy one space, that move through space and time in a scientifically studyable way. So ultimately what Physics 204 is about, it's about the same principles and practices of physics, but it's about those type of entities, those type of immaterial entities like waves, fields, and radiation. Okay, that's what this course is actually about, even though it still might not feel that way yet. And all of those things, sound wave, water waves, sound waves, electricity, magnet, at the heart of all of them, the way that they can exist and the way they can be scientific phenomena that are studyable but are not made of particles, is that what they all in the end are systems that center on harmonic oscillation. The way, well, right now we are intensely focused on harmonic oscillation right now, because once we understand how one particle can move back and forth in a manner that we are now calling harmonic oscillation, if you put a bunch of particles together and have them all harmonically oscillate in a very specific pattern or in a very specific organization, that is how you create these waves and fields and radiations and these seemingly abstract phenomena that are not particular but are real. That the heart of turning particles into information, the way to do that is to get the particles to vibrate all in a big organized group. So the fundamental ingredient of this class is this type of vibration called harmonic oscillation. As long as we understand it, we can understand all these abstract entities like sound and electricity and light. Last thing. Oh yeah. you know, so what I'm trying to argue is that it's still physics. It's still the study of the world. It's still the study of motion. Only now the entities that are moving are more abstract than they were last semester. And because the entities themselves are more abstract, the mathematics needed to describe them starts to become more abstract. This is why Physics 204 is a more advanced class than Physics 203. For my money, ultimately, at this stage of my life, I think it's that much more exciting. I think it's amazing that physics can deal with these things and deal with it in the way that it does. But that's your choice. But that's the point, is that we are now unpacking the mathematics of harmonic oscillation so that we can study unthingy things, so that we can study not how particles undergo trajectories, but how information flows. Okay, so to get back to harmonic oscillation, we'll get back to homework 2 now. And the goal is, I think now we finally sort of have the mathematics of oscillator. The next step is we have to figure out how we could put one oscillator next to another, get a bunch of oscillators, and hopefully in our minds and in the lab, create a wave. That's where this is going. That's the purpose of all of this, just so you know. So we're not just doing math for math's sake, even though I would be perfectly happy with that too. So that said, we're going to turn to homework 2. I'm going to screen share to show exactly where we are. And I'm going to start moving faster in homework 2. Hopefully I did the first example a couple days ago. I mean, the first exercise, and I did it with the 5-step method as I want you to do it. So now from here on in, I'm going to go a little faster and just like like give answers and stuff. Oh, so you should stop me at any time, really, and say, like, how did you do? I don't know how you did that or how'd you get that. But if you don't, I'm just going to sort of move faster. So I'm going to start. I'm as far as I know, we got as far as 1A and B. Like we got that far. We got to B last time we talked about it. So now I'm going to start with part C and move from there. And I'll say right now too, I mean, I'm obviously going to switch the screen in a second. I'm going to start with C and do D, but C and D in themselves are almost like out of order. Like the only way you could really answer C is if you do D. So it's sort of just asking you to show your work in a way in D. I don't know why it's in that order, but so I'm going to do C and D right now. And then E is very redundant. I'll just give the answers. And then, but I really want to talk about F. F is what's going to get us into multiple oscillators. So, okay. So this is what we're doing. If you have to screenshot it or whatever. So C. Okay, so bear with me. I'm switching the screens. I'm switching the notes. And someone's here. Wait, hold on. Okay. So again, I'm not, you still have to do the steps and all that. I'm just trying to like go faster here. So stop me anytime. But this question C is that function a solution to that differential equation, right? Now, I'll tell you right now, I say the answer is no, but the way I get it is actually by doing D. Okay, I say no because, okay, so I'll do, okay. So tell me if you need me to go back on the board. But the way to know, the way to say yes or no is to take derivatives always. So, which it asks me to do in D. Again, the function was x equals a cosine, um, a cosine of 5t. So I'm going to take a derivative, taking one derivative, and you have to show all the, well, whatever. Stop me if this is not comfortable. That's one derivative. And then if I take another derivative, oh, sorry, that's a joke. That's a joke. I'm just joking. It's that. Okay, now if I take another derivative, funny joke, right? It looks like this, right? So now I look at it and I'm like, is this x? No. X equals a cosine of, I mean, oh my God. Sorry. Well, yeah, yes, that is x, but sorry. The question is, sorry. This is x. But the question is, does d2x dt squared equal negative 3x? I mean, that is the question, right? Right. And so there's x and there's x. But the problem is that 25 does not equal 3. Like literally, like the answer is no. The second derivative with respect to time, the second derivative of x with respect to time does not equal negative 3 times x, because apparently the second derivative of x equals negative 25 times x. I mean, it's that straightforward. Like, so the answer is no. 3 does not equal 25. And this is just to emphasize. So the answer is no. And you please, I'm switching screens back and forth here, so feel free to ask any questions in the chat. But the answer is no. And this is just an exercise to show two things. Like one, the answer is not always yes. Like you do have to take derivatives to find out whether something is a solution to a differential equation or not. And more to the point, just because something is a cosine, like just because something has that form of cosine, that doesn't mean it solves that differential equation. To be more specific, well, I guess what I'm really saying here is, the thing that I'm really trying to say is, the differential equation described a simple harmonic oscillator, and the proposed solution described a simple harmonic oscillator. Like the equation and the solution are both simple harmonic oscillators, but they are different simple harmonic oscillators. The cosine expression described a simple harmonic oscillator with an omega of 5 radians per second, right? And a simple harmonic oscillator going wiggling back and forth at a rate of 5 radians per second, which is a little bit less than 1 cycle per second. How do I know? Because there's about 6 radians in a cycle. 2 pi is approximately 6. Like I'm approximating just to get a feel. But something that's going back and forth at 5 radians per second is going back and forth a little bit less than 1 cycle per second. So it has a little bit more than a period of 1 second per cycle. The other oscillator is a simple harmonic oscillator with an omega of square root of 3 radians per second. Where did I get that from? Because 3 is the constant in the differential equation. That's what we, right? This is like the takeaway from the beginning of yesterday, Monday. Like, that does describe a simple harmonic oscillator, that differential equation. But it describes a simple harmonic oscillator whose omega is the square root of whatever that proportionality constant is, in this case, 3. So this is an oscillator that's oscillating less rapidly than the other one. They're not the same oscillator. So it's not a solution. I think something just happened in the chat. I'm going to look. Hold on a second. Not the same oscillator. But they are both oscillators, and they're both harmonic oscillators. So that's just to reinforce that, to clarify that. Oh, no problem. Okay, got it. Chat person. Okay. Okay, so I'm gonna go, unless there's questions, I'm gonna move on. That's that one. In fact, I'm even gonna say the next one, I'm not even gonna. We've done it so many times now. I mean, okay, I'll just write the answer, but I don't think there's much to say about it. It's just again trying to reinforce that sometimes, for a mass on a spring, omega is k over m, but for a pendulum, it's like g over l, whatever. But here, so I'm just gonna write the answer. It's like the derivative of that. It's just practice. So the derivative of that is negative a sine. Oops, sorry, no, it's not. It's just practice. Negative a k over m sine of negative k over m t. Again, if you were doing the homework, you'd be showing all your steps, but I'm just telling you. And so and I don't know why the Roman numerals went 3 and 4. That's just a typo that I never fixed. I apologize. So dt, take the derivative again, it's going to be negative a k over m cosine. And you could rewrite this. Multiplication is I know there's someone in the waiting room. I'll get them in a second. Multiplication is commutative. So you can switch the order around. So that's it. Those are the answers. I know there's someone in the waiting room. But who cares? Not who cares if there's someone in the waiting room, but those are the answers. But just by doing that, you can see that solves the differential equation for the original Hooke's law spring. So those are the answers to that. That's just like review. I'm just looking at the chat. Okay. But now things, again, you can stop me. But if you don't, I'm going on to the next one where it gets a little bit more interesting. So now F, it says given x equals a cosine omega t plus 3.5. So that's a slightly fancier, more complicated expression, right? And it says, so now, and again, the Roman numerals are off. I don't know why, but it asks, what is the first derivative of that? Right? Okay, so it's a new expression. It's just asking me to do a derivative. 3 point, no problem. Thank you. Derivative, derivative 3.5 is just a number. It's a constant number. And I'll tell you, there's nothing special about it. It's just a constant. So if we take the derivative of this, and you should stop me if this is not clear, but I think, again, if I were doing my homework right now, I would literally say, the derivative of cosine is negative sine, and the chain rule applies, like we're doing a function of a function. In fact, I'm going to say this. I should probably write it down, but we're doing chain rule again, function of a function. The inner function is omega t plus 3.5. The derivative, oh, hello, Bridget. Sorry, that's nice. I didn't even see that. Hello. The inner function is omega t plus 3.5. The derivative of that function is omega, right? I mean, technically it's like omega plus 0, if you like. but the derivative of that inner function is the same as what the derivative would be even if the 3.5 were 0. If you, okay, and you really should stop me if that, or put in the private chat if that's not clear. But it seems to me what I'm saying is that that's the first derivative of this. So the new function was fancier than the functions we were looking at up until now, but the derivative is not any fancier. That's what I'm saying. And then if we do, then it wants the second derivative. Second derivative, same thing's going to happen. Like chain rule still says that the derivative of the inner function is just omega. So again, only an omega comes out. And the function, and the derivative looks like that, right? Okay, so that's the answer, first of all. I'm just looking at the chat. Okay, but then it asks sort of the key question here, G, it says, is A equals cosine omega t plus 3.5 a solution to d2x, right? Right. And let me say, right, that's the question. Is that cosine thing, which is fancier now, a solution to our standard differential equation that we're getting used to? So, right, I mean, the one and only one that we have so far. So another way of putting this question, just to be clear, is what we're asking is A equals cosine omega t plus 3.5 a simple harmonic oscillator, right? Or does it describe? And I think the answer is yes. Because, well, wait, did we get? Yeah, because, well, here, I'll just recopy. Because we just said, we said, we just found that d2, the second derivative of that x equals negative a omega squared cosine omega t plus 3.5. And if you just rearrange it, multiplication is commutative. You could say omega squared a cosine omega t plus 3.5. And this whole business, right here is x, right? So yes, so the second derivative of this x that we're trying does equal negative omega squared times x, right? So the answer is yes. And here's the point, like, so what? The question, the homework doesn't say so what, but the question I'm asking is like, why did the homework assign this? Like, who cares? Here's why I care. Because what we finally, hopefully, sort of got straight Monday when I was trying to drive home Monday is that from now on, whenever you see that differential equation, you should think, aha, that's the differential equation for simple harmonic oscillation. And what we were saying as of Monday is, aha, the way to predict a simple harmonic oscillator, the solution is x equals a cosine omega t, or x equals x naught cosine omega t, whatever, some cosine omega t. Now suddenly we're saying, wait a minute, that was true. Everything we've said up until now is true, that the cosine expression we have is a solution to the differential equation. But now what we're realizing is, wait a minute, it's not the only solution. It's a solution. It's not the solution. We're realizing now in general. Okay. What I'm saying, hold on, let me switch back to the screens. Anybody here? Okay. What I'm saying is, what I'm saying is, uh, we we finally got straight that the cosine solution like works, and we've to solve the differential equation for harmonic oscillation. And we've been saying, okay, if we're talking in general terms, like where the variable is just called z, because I don't know if it's x or if it's theta or what. In general terms, if the variable is z, we've been saying z equals z naught cosine omega t. Now what we're realizing right now is actually every time we've said cosine omega t, really what we were tacitly saying was cosine omega t plus zero. We were like not adding anything to the omega t in the parentheses. But it turns out we just tested today, just now. It turns out we could have added any number. It didn't have to be zero. We could have added any number to the omega t, and the derivatives would still work out the exact same way. So even if you throw an extra number into the parentheses, you still have an expression that satisfies the differential equation. So we now have to be careful, or we've now learned that the solution is more general than we realized. That any number can be put in the parentheses as long as it stays constant. I mean, as long as it stays constant, so the derivative of it is zero. So from now on, we're going to put an extra term there. That term is the lowercase Greek letter phi or phi. We're going to put that there, and it can stand for any constant at all. And it can be positive or negative. You can say plus or minus, it can, whatever. It can be positive or negative. It could be zero, but it doesn't have to be zero. Um, and and we're going to actually have to account for that in our solution. And before we go any further, since we're scientists and all of these things, right, it's not just raw math, it all means something in the experiment or the phenomenon that we're observing. We got to make sense of what this phi means. Like the math just said that we can put it there. In fact, the math just said that we need to put it there. But now the question is, as a physicist, like, okay, what is it like? I mean, omega means how quickly the system is cycling, and z naught is where the system started. Like everything means something. So what does this phi mean? And the first way to get at that is the same way we got at what omega meant, is let's think about units of measurement. So I'm actually going to ask, because strangely we still have 40 minutes in class, I'm going to ask you in the chat, let's say private chat. So no one, just put in the private chat a guess, a conjecture. And if you're really paying attention, by the way, I don't even think it's a guess. I mean, I think you can get this right for sure if you want to, but I would like to see in the direct chat what units this phi must be measured in for all of this to work and make sense and be self-consistent. So I'm going to pause. I want you to put in the direct chat a guess, or you can write in the direct chat, I am paying attention, but I have no idea, or something like that. Okay, I was just, great. I just saw one person in the chat, and awesome. Thank you for paying attention. And I'm not going to say right or wrong yet. I was just going to say once I get 3 people in the direct chat, like right or wrong, then I will go up 2 people. Okay, thank you. Okay. Oh, great. All right. Oh, a lot of people in the chat. Great. And every one of you put in the chat, you should definitely submit for points. Like it really helps me a lot. I like when we do this. So I've got tons in the chat. I'm going to read, and they're thoughtful. Okay, I'm just going to read them out loud just so you know. Uh, these are what I hear. I hear degrees. I hear I am paying attention. I am paying attention. Radians. I'm not sure right now. I am paying attention, but I'm not sure. I'm paying attention. LOL. I am paying attention, but I'm not sure. I'm paying attention, but I have no idea. I actually really do appreciate that. Really. I mean, I bet if you, fair enough. I'm not even, thank you. It means a lot. You should definitely submit for more. I'm paying attention, but I just came back from the bathroom. Okay. Probably didn't want me to read that out loud, but okay. I'm not sure. Degrees. I'm paying attention, but I have no idea. Okay. Diameter. Interesting. But I'm paying attention. Radiant. Oh, and then when the public chat. Okay. I meant for that would be the private chat, but okay. Cool. But thank you for having the guts of going in the public chat. So, a lot of honesty, thank you, and a lot of participation. I appreciate, and well, to cut to the chase. Some people said degrees. I think that's very smart. Degrees make sense, and technically it could be degrees. And how would they know degrees? Because you can't take the cosine of other things. You can take the cosine of an angle measured in degrees. The only thing I would say is to the people that said degrees, like we're now in a context of physics and math where we're doing everything in radians. So whatever logic you use to get to degrees, I agree with the logic, but I would say radians is more the direct thing that we're doing now. Diameter was very smart, by the way. Okay, and you, the person who wrote diameter, you should submit with all due respect. It's not right. So you should submit to the wrong portal but it's a very good wrong answer. Like it shows that you've been paying attention to all the stuff to say diameter. Because a big point that I'm trying to make to all of you is that an angle is just a section of a circle, and that what we care and everything in physics we're doing is we're looking at cycles and we're using the math of circles to describe the physics of cycles. And the reason we're doing that is that what they both have in common is any things that are constant about circles don't care about how big the circle is. Like a 90, a pi over 2 radian angle, or a right angle is a right angle no matter how big the circle is that it's cut from. It's a quarter of a circle no matter how big the circle is. And similarly, a harmonic oscillator has an omega of 4 radians per second for, like a certain number of cycles back and forth per second, regardless of how big those cycles are. Okay, so it's very smart that a person said diameter, but what I do think is that the answer is radians. And I think that not only because you can't take the cosine of anything but a degree or a radian, but also omega t was already in radians, right? Like omega is in radians per second, so that the seconds cancel out with the t, and you're left with radians being omega t, and that's how we took a cosine of it up until now. So the only thing you can add to a radian is another radian, or the only thing you could subtract, like, is right. You can add kilograms to kilograms, but you can't add meters to kilograms. I hope that's clear. So I do believe, and I see there's more in the chat. I'll get that in 1 second, but I do believe, yes, the measured in, so the units of this phi must be radians, whatever it is. So it means something that's measured in radians. I see something's in the chat. Hold on. Good. Right. In the direct chat, paying attention. Oh, and thank you. Paying attention, radians. Cool. And I was going to say, because omega is angular, I would technically say they wrote omega's angular velocity. I see in some contexts in physics it is. I would say here it's angular frequency, just to be clear. Like it's angular frequency in this context, but yeah, and angular quantities are measured in radians. Absolutely true. Yes, I'm good. So it's radians. So So from now on, we have this new constant to deal with. And this thing is called the phase constant. Whoa. Okay. Wait, look in the chat. Okay. From now on, this phi thing stands for some number of radians. It might be zero, it might not be zero. And what the number of radians is some kind of head start or delay with regard to the cycle. So it's like this phi thing is like, well, loosely like if you remember, if you thought of it this way, our old equation x equals 1 f at squared plus v naught t plus x naught, if you thought of it that way, depending on like, where you took physics or whatever, that x naught was like initial position. It was like where the thing started before all the activity, where it already was placed when all the activity and timing and everything began. So this is like that. Phase constant is like the initial position of the oscillator, only it's not the position of the oscillator on a meter stick. It's not position of the oscillator. It's not where the oscillator is in space. It's where the oscillator is in terms of its cycles. Technically, a phase is a moment or a snapshot or a cross section or a portion of a cycle. So to have a phase constant means where you are regarding the phase. Let me be more clear. Okay, but that's what it is. It's like if an oscillator starts somewhere into the cycle already or is delayed, cycles are cycles, but basically the phase constant is how much of a head start or a delay does the oscillator have with regard to a full cycle? Okay, what do I mean by that? I mean, okay. In our original, so what this says in my handwriting is when phi, so just to give you to let you understand what phi means, let's go to the extreme examples. Like if there is no phi at all, if phi equals zero, the examples that we've been doing so far, what that means is there's no head start or delay. It means that the oscillator began at what we traditionally consider to be the beginning of the cycle, i.e., the person started their stopwatch when the oscillator was all the way at its maximum displacement from equilibrium, right? As was the case all the way through homework 1. Like in homework 1, when the mass was at 15 centimeters from equilibrium, right? That's what we call T equals 0. Like it might have already been going back and forth for a while, like in the lab, like it might have been doing this and this, but you started paying attention and you started your stopwatch right when the thing got to its farthest possible displacement from equilibrium. In the case of homework 1, it was 15 centimeters, right? So you start your watch then, it's all the way out there, and then it goes all the way, it goes to equilibrium all the way to the other side, and it comes all the way back. It does a full cycle, like from head to middle to tail to middle to head, so to speak, right? That's what we would consider no phase constant at all. No head start, no delay, no fancy business. We started our stopwatch at the amplitude position. So look at the math for a second. In that case, i.e., hello, i.e., when t equals 0, sorry, i.e., when phi equals 0 and t equals 0, if x equals x naught cosine omega t, sorry, let me just. If that's 0 and that's 0, right, then x equals x naught cosine of 0, which means x equals x naught times 1. So x equals x naught, right? Just saying, when I first, it may look like I'm going in a circle, but I'm just saying, like, what it means to have a phi of 0 is it means that when t equals 0, x is at x naught. The thing is at its amplitude position when we start the stopwatch. That's if phi equals 0. But now to understand the meaning of phi, let's do a different example. This is all me teaching, right? This is not a homework. This is all based on homework D or whatever that question was. This is the purpose of that 3.5 question, is to launch us into an understanding of phase. Okay. So 3.5 was just an arbitrary example. It didn't matter. It could have been 4.7. Like, okay. But for example, when phi equals pi over 2 radians, pi over 2, right? If phi, for example, is pi over 2, totally, that's a completely reasonable, common thing that phi could be pi over 2. What would that mean? Well, I'm going to tell you right now, I think in English, what it means is this means we started our watch, our timer, when at the moment that the oscillator was 1/4 of the way into its cycle or behind its cycle, depending if it's positive or negative. Sorry. Into its cycle. Okay, first of all, I'll say, if we say that phi is pi over 2 radians. I submit to you, and I'm about to prove it, but I submit to you that means that the oscillator had a quarter cycle head start or delay, i.e., we started our stopwatch not when the thing was at the beginning of the cycle. We consider amplitude the beginning of the cycle, not when the thing was at amplitude, but when it was a quarter of the way into the cycle. Now, where did I get a quarter from? Hopefully, if you're following this, I say a quarter because one cycle is 2 pi radians. So pi radians is a half cycle. So pi over 2 radians is a quarter cycle, right? I.e., like 2 pi radians. You always want to remember that. The whole key to this whole thing is that 2 pi radians means one cycle. Or conversely, a radian means approximately a sixth of a cycle. If you can really get your mind around that, like everything like goes around that, I believe. So if phi if the phase constant is pi over 2 radians, then that means we're a quarter of the way into the cycle already. When we started our stopwatch. And what I mean mathematically rigorously, or to show you, I mean, in other words, if phi is pi over 2 and t equals 0, in other words, I'm going to test now. If phi is pi over 2, where's the oscillator at the moment I start my stopwatch? Well, just do the math. Like x equals x naught cosine omega t plus phi, right? So I'm just plugging in. So x equals x naught cosine omega, and I don't even know what, it doesn't even matter what omega is. Notice that. I'm just proving, I'm asserting things that are true about phi, regardless of what omega is. Omega times 0. Well, I'm sorry, I guess I'll do it the same way I did before. Sorry. So t is 0, and phi now is pi over 2, right? So we get x equals x naught cosine of 0 plus pi over 2. Okay, so the cosine of pi over 2, I'm going to do it again. It's 107. In the direct chat for more points for eternal love flowing from me in a completely professional way. In the direct chat, could you please put what is the cosine of pi over 2? And I mean, you could use a calculator. How would I know? But I would challenge you to try to not use it. Ooh, that was fast. One person got it fast. I'm not saying the answers. I'm not even saying it's right. I'm just saying it's fast, although it totally is. It totally is right. Good. Okay, there's 3 people in the chat. But in the direct chat, please. But okay. So I'm not saying right or wrong, but just go in the direct chat. I mean, go in the chat. I'm seeing a lot of answers. Good. Again, the question for those people who are tuning in now: what is the cosine of 0? No, that's not the question. Sorry. The question is, what's the cosine of 0 plus pi over 2? What's the cosine of pi over 2? And okay, I'm seeing a lot in the chat, and I really appreciate how much you're all paying attention and you know the question. And good for you that you at least knew this was a simple question that you could take a guess on, even if it was wrong. I really, those of you, I'm going to say the right answer in a second, but if you got it wrong, you should really, well, either way, you should submit for points. But if you got it wrong, you should really submit to the portal that says be really, really wrong. Like really. Because so I see, I'm just gonna read the answers. I see 0, I see negative 0.5, I see 0, I see 0, I see 1, I see 1, I see 0, I see 0, I see 0, I see 0. Very good. I see 0. I see. Oh, you're correcting yourself. Okay, someone just corrected. Fair enough. That's fine. That's totally fine. You can submit twice if you want. So yes, so I will say this. If you're going to memorize anything or try to get, because this is going to come up a lot. You see, it comes up all over the homework. Blah, blah, blah. We care about cosines and sines now a lot. We care about them in physics a lot. So, I mean, I certainly highly recommend the unit circle. I mean, some of my best, I love the unit circle. Like if I opened up a restaurant, I would not call it the unit circle, but I'd want to. Um, uh, But if you can't deal with the unit circle, just memorize this at least. Sine super, cosine crappy, or sine super, cosine counterintuitive. The sine, I know I've said this to some of you before, but the sine is the one that does the thing that you would want it to do. The sine of zero is zero. You can just memorize that. It's like a snake. It's like all S's. Sine of zero is zero. And sine is the thing where when the angle is small, the sine is small. And as the angle gets bigger and bigger, the sine gets bigger and bigger. If you were inventing a function on a desert island, it would look like that, I think. I mean, if I were, right? Sine is super. As its sine of zero is zero. As the angle gets bigger, the sine gets bigger. It's cosine that is counterintuitive or crazy, whatever you want to call it, that begins with a C. Cosine, the cosine of zero is one. And then as the angle gets bigger and bigger, the cosine gets smaller. Now, it's not really crazy. I mean, if you think about the unit circle and you think of the cosine being the x coordinate, it all makes sense. But point is, sine of zero is zero. You should remember that for the rest of your life. And cosine of zero is one. I'm not shaming you for not remembering. I'm saying from here on in, remember it. So, yes, I agree with those people in the chat that said the cosine of zero. Sorry. The sine of zero is zero. Cosine of zero is one. So the cosine of pi over 2, the cosine of a quarter of a circle, the cosine of 90 degrees, the top of the unit circle there, that's what is zero. I mean, cosine ranges from 1 to 0. That wasn't even a good explanation, but it's the case. So I'm agreeing with those of you who said cosine of pi over 2 is 0. So what? So what that means is step back and I just did the math to make a point. Step back and look at it. If the phase constant is pi over 2 radians, what that means mathematically, if you just plug in like I just did, what that means is that at t equals 0, the oscillator is not at x naught, it's at position 0. What is position 0? That's the equilibrium. Right? And this, to me, this makes sense. In other words, a full cycle is there and back, like all the way there, all the way back. That's what a full cycle is. A half, and what do I mean by here and there? Here is like amplitude, there is negative amplitude, right? So a full cycle is positive amplitude, equilibrium, negative amplitude, back to equilibrium, positive amplitude. That's a full cycle. That's 2 pi radians. A half cycle is positive amplitude all the way to negative amplitude. That's a half cycle. There, but not back. That's pi radians. What's half of that? What's pi over 2 radians? From amplitude position to equilibrium position. A quarter cycle means go, right? So if there's a phase constant of pi over, this is just an example, but to show you what phase constant means. If you have an oscillator that is x naught cosine omega t plus pi over 2, what you're saying is it's a regular oscillator, just like the other one, has the same angular frequency as the other one, all that stuff. But this one, I didn't start my stopwatch when it was at amplitude. I waited until it was at equilibrium to start my stopwatch. That's what it means. If phase constant were pi, then it means I started my stopwatch when it was all the way at negative amplitude, etc. So phi, the phase constant, is an indication of a head start or a delay in measured as a portion of the cycle. Where were you in the cycle when the stopwatch started? That's what phi measures, and that's what we now from here on in always can and must keep track of. I'm looking at the time. Okay. I will go back to the homework in a second. One last thing. Okay, question. Before I go back to so this is very important, this phase constant thing. Very important. Question that may or may not be on your minds. I kind of hope maybe is. Like, why do we even need it? Like, hopefully it makes sense to you, but you might be saying, especially if you've gotten used to physics, like, okay, but we got away with it up until now, not having one. We got away with it in two labs at least, not having one. And we got away with it because we just like decided to set things up so that we started our stopwatch at the most logical time, the time when the moment when the oscillator was at amplitude position. We started our stopwatch then, and therefore phi was zero, and we didn't even have to think about phi. We didn't even have to know about this as long as we started our stopwatch at the most convenient time. Why don't we just like always do that? Isn't that what physicists do? They make the choice that is the most convenient and yes, that is what physicists do. And yes, that is what we got away with two labs. And yes, as long as we can do that, we should do that. But we can't always do that. The answer is we can set phi equal to zero as we've been doing if and only if, right? IFF means if and only if we only have one oscillator. The whole key to this phi, why we need this phi, is so that we can handle multiple oscillators, which we totally want to be able to do. So what it says in English, it says if and only we can set phi equal to zero if and only if we only have one oscillator. But once we have multiple oscillators, we have no right to assume that they'd all be in phase, that they'd all have the same phi. So we could start our stopwatch and match with one of the oscillators, but unless all the other oscillators are literally always in the same space at the same time, then some of them are going to have non-zero phis. And by the way, if all the oscillators if they all are in phase and are all in the same space, or in the same coordinate at the same time, then honestly, that's a stupid setup, because then why do you have multiple oscillators? You might as well just have one big thing going like this, right? So once you have a bunch of oscillators that are not in phase with one another, which is really ultimately what's going on in lab 3 and 4, and you're using these oscillators to make unthingy things, then in order to track one oscillator relative to another, you need this phase constant. Or put another way, in order to organize the oscillators in a fashion that will allow us to make an unthingy thing, you need to organize the phase constant, in a very specific way. So that's why we need phi. And that's where we're going to go from here. That's what's ultimately happening in lab 3 and lab 4, which I guess you probably already have done lab 3. Well, anyway, we'll talk. But we have 10 minutes left. So I think just for the sake of like organization, I'm going to go back and do a little bit more with homework 2 now. We may not, in fact, but yes, we may not do all the exercises together of homework 4, but in fact, wait, let's see. In a way, I'm just looking 1 second at the. Well, okay, yeah, no, I'll just keep going with homework 4. Okay, so we have 10 minutes. Just gonna do a couple more exercises from. So that was all like that was not off the topic. That like is the topic. That was the purpose of question F. But that's my instruction to you. I was not expecting you to write all that down for the homework or something like that. Or that was question G as well. So now back to um, okay. Now I'm really now there's 9 minutes. I'm going to just do a couple exercises, but you really need to stop me in the chat if I'm about to do some calculus things that I'm sort of just assuming that you remember or know from calculus, but you might not. So you should tell me. But I now have this totally different function, e to the negative omega t, totally different function. And it's just asking me to take derivatives and play with it. Why? I mean, why are we suddenly like looking like a math class? Well, because remember because I'll say. Okay. The reason all of a sudden we're like jumping, like naming a whole other function here is because the takeaway of exercises F and G is that we just found out that the cosine omega t, cosine omega t, cosine omega t that I've been saying for a week, that does work. That does describe a simple harmonic oscillator, but apparently it's not the only thing that works. We just found out that you could add a phi to it, and that still works. So now our brain is going, my brain is going, oh, so wait, my journey's not over. Like, there may be totally other ways to describe a simple harmonic oscillator, and maybe they have other conveniences or advantages or capture physical information that I'm interested in. And so I'm now trying other functions to make sure. And I'm not trying random I mean, it looks random, but I'm not just trying random functions. I'm not going back to 1f at squared or something like that. I'm trying functions where I know that taking derivatives of them eventually gets them back themselves. I'm trying what are known as transcendental functions rather than algebraic functions. Right. So this E looks like it's out of nowhere, but it's not really out of nowhere because okay, I'm just reminding you again, the given is x equals e to the negative omega t. And the question was, what is dx dt, right? Well, you may recall I guess I'll say, if this were a step 3, remember, in general, this is where you have to stop me if this does not make sense, but in general, in math, right? If y equals e to the x, then dy dx literally equals e to the x, right? Like that's actually like that, that's like we could have months of discussion on that in itself. But e to the x is that function for which the derivative is literally itself. And if right, I mean, what's a derivative of e to the x? E to the x. Now you might say, why? Good question. And we could talk about it for a long time. I'd love to talk about it for another time, for a long time. But the one thing I'll say for the moment, since it's a physics class and we have to move on and stuff, one thing I'll say for the moment is maybe that's the wrong question. Maybe a better way to put the question is, now that I understand derivatives and I understand that some functions have rates of change that seem to return back some aspect of the function. Now that I understand in life that feedback happens, that sometimes your position is based on your acceleration and your acceleration is as well based on your position, right? What you might do is just step back and say, is there any function Like, what is there a function that just purely captures that idea? Oh, great question. Okay, I see the chat. Hang on one second. Like, so if you ask the question, once you realize that there are phenomena where the input feeds the output and the output feeds the input, and it feeds back like that, and you see that cosine and sine are variations on that theme. They don't do it exactly. Cosine does not literally return, like the derivative of cosine is not literally cosine. It's negative sine, right? But then the derivative of negative sine is negative cosine, and then negative cosine is sine, and then the derivative of sine is cosine. Like, so eventually you get right. So there are functions like cosine and sine that sort of do a variation on this. But if you were ever to ask, isn't there a pure form? Like, isn't there just like a simple, pure elemental case? Or is there a way to describe the base idea of a function that just directly feeds itself? The answer is yes, we call that the exponential function. Like, it's not so much why does the exponential function do that? It's the exponential function is our name for the purest form of that idea, I mean, if that makes any sense. Someone in the chat, so um, and I could literally go on about this for, I mean, it's a really exciting idea. Um, Someone in the chat is saying, are there any other functions that do this? There's tons of functions that do that. And there's an infinite number of functions that do this, just like there's an infinite number of functions that don't do it. I'm not being glib, but I'll say this, there's two families of functions in the world: algebraic functions and transcendental functions. These that we're talking about here, these ones that feed back on themselves, are called transcendental. And there's tons of them, but all of them, in the end of the day, are based on sine or cosine, and sine and cosine are like basically the same thing, just right. So they're all, at the end of the day, based on either cosine or e to the x. And it does turn out that e to the, you may know this, the person who's asking the question, it turns out that even e to the x and cosine can be expressed as versions of each other. We'll get to that in a minute. But like, so at the end of the day, the root to the whole thing of feedback is e to the x. That is what we mean by exponential. Okay, well, let me just, so there's a lot more to be said about that, but great question. So just to finish this problem, so then it asks, sorry. So what is the derivative? So the derivative involves that, but involves chain rule as well. There's chain rule going on here. So I'll just cut to the chase to finish the problem and to dismiss us all. Thus here, so if I were doing step 4 now, thus here, dx dt in this case equals negative omega e to the negative omega t. That is so sloppy, right? Because of chain rule, like the negative omega came out. So that's the answer to the first derivative. Oh, it's 128, so we can quickly do. So then the second derivative, I'm just going to say quickly. I will say more about this next class, but then the second derivative is just do that again. So it's negative omega squared e to the it's omega squared, right? Because the negative comes out again. So that's the second derivative. And the conclusion of that, did it ask? Yeah. So then on I, is it a solution? The answer is not a solution. Close. It looks like it should have been. I was curious. I'm interested. I'll talk more on Monday. I thought the idea of the E would be good, but the problem with the E is the E itself never returned a negative sign. The negative omega from chain rule gave a negative sign, but it did so twice. So the negative sign canceled itself out, which is not what happens with cosine, right? So in the end, we don't get, it's close, but there's no negative, there's no restoring force here. This is not a simple harmonic oscillator as written. So the answer is no. All right, but that's, right, okay. I want to talk more about this on Monday. I'm glad the person asked, are there other functions I want to say more about like that? Or I could privately talk about E and how exciting it is. But that's as far as we'll go today. It's 1:30. Thank you all very much. Pause for questions, but have a good one. Just stay abreast. Have a nice day. Yes, have a good day. Thank you.